Hey, folks. Glad to see everybody here. I'm Guy. I'm the CEO of Fhenix. We build privacy rails for payment, stablecoin, and DeFi applications. And I'm going to talk about the need for transitioning from transparent by default to private by design, and give you like a glimpse of the different primitives that we're using today in Ethereum ecosystem to provide confidentiality. I think the first thing that I want to talk is like, why privacy? We've been talking a lot in the last couple of days about different privacy technologies, but I think we want to start by understanding what is the value, and actually, what have we seen in the last 2 years around privacy? And I do feel that when privacy just started, it was more of a technology that was trying to find like a product market fit. Thinking about what happened in the last year with the growth of stablecoin adoption, the payment space, the institutionals that are moving into Web3, and even the transition from a semi-idealist kind of approach to more of a pragmatic approach, the need for privacy became prominent. You cannot do a payment application with stablecoins with everything is like public by design. And that is a really good thing for us privacy companies, but it actually also drives a lot more demand. Having said that, we're in 2026, and you would imagine that many people still understand the difference between anonymity and confidentiality. This is literally like a Telegram conversation that we have with a team that's building on us, and this is like from 2 weeks ago when they were asking us, okay, so we're building on you guys, but are we getting just confidentiality or also anonymity? And that's when I said, you know what, maybe this would be a good talk here to just give an overview of the difference between anonymity, confidentiality, and the different primitives that are there to solve it. So, important to mention, privacy has 2 dimensions, anonymity and confidentiality. Anonymity, hiding who you are, that's a core narrative on the Web3 ecosystem, and then confidentiality, which is more about hiding the content of the transaction. I'm not going to talk a lot about anonymity. Actually, I think the previous talk did a good job. But just to make it very, very clear, we're talking about the ability to hide the identity of the user, so the sender and the receivers are unknown, and this is typically achieved through techniques like RIC signatures, zero knowledge, stealth addresses, and mixers that are out there. Railgun and a few others are really doing an amazing job in that respect. We're here actually to talk about confidentiality or transparent by default. I'm sure this is a privacy session. Everybody here probably knows everything on the blockchain is transparent by default. You have a block explorer. You can actually see all the content of the transactions that are out there. So let's look at an example. And this is the typical transaction life cycle. We have the transaction being submitted, and then the transaction being ordered and the sequencer, and being executed. The key challenge is that since everything is out there in the public, this is a really good opportunity when the transactions are being ordered to extract MEV. A malicious actor, Bob in our case, can actually see the transactions in the mempool and can front run them to achieve MEV. The problem is not so much just about encrypted mempools and transaction ordering. It's also about like how do we solve it, and the way to address it is by offering an encrypted mempool. If the transaction is encrypted, then the malicious actor can see the content of the transaction in the mempool and cannot front run it. So the order that you would do is you would encrypt the transaction on the user side, you would bust an encrypted transaction, a transaction would be committed, and only then after the block has been finalized, you would decrypt it and execute it. So encrypted mempools, definitely a way to mitigate MEV. Another example is sealed bid auctions. This is like a typical example that we always like to give when we're talking about confidentiality. It is quite easy to understand that if you're bidding and your bid is out there in the clear, then anybody who can see the amount that you've bid can just provide a higher bid and just win the bidder. And this is definitely not ideal for the person who's participating in the sealed bid auction mechanism. We've seen the demand for like sealed bid auction growing quite a lot in the last couple of months, with also some launchpads that are using it for public sales for community. The way to address it is, again, by having an encrypted transaction. The encrypted of the transaction is part of the bidder's proposal, and in that case, the competitors can see the amount that you've bidded, as such, cannot really like offer an alternative. And this is really good for like price discovery for both the bidders and the auction organizers. In both scenarios, the order that we follow is encrypt the transaction, compute over the transaction, and then decrypt the transaction. Okay, so how do we solve it? There is like a 3-letter acronym salad: TEs, MPCs, FHEs. I'm gonna walk briefly through each of them, and then at the end offer like a framework if you're building a confidential smart contract of like what type of decisions you need to think about. So just so you all know, in my previous life, I actually managed the team at Intel that was responsible for building TEs. I love TEs. I think they're great. I think they're extremely valuable. And typically when you want to operate with a trusted execution environment, it allows you to compute inside a trusted hardware. So the flow that you would execute is that you would take the transaction or the data that you want to compute on, you would encrypt that data, you would send that encrypted data to the trusted execution environment, in which it will actually be decrypted and compute as a decrypted content inside a trusted execution environment, only for then to have the computation result encrypted again and sent back as a result. It's very fast. The computation is extremely fast. It's very cheap, but the key challenge is that it's also prone for attacks. And for those of you who follow the TEE space, about 2 months ago, researchers showed that by just building a hardware device in less than $1,000, they were able to listen to the memory and extract keys from the trusted execution environment. How do you mitigate it? In most of the attacks around TEEs, typically you need your hands on the physical hardware itself. So if the TEEs are managed in the cloud, and this is where proof of cloud is coming in, that reduces the risk quite a lot. Open sourcing the TEEs, making sure that you see that the code of the TEE itself is secure, definitely helps. And also like a multi-vendor strategy. But the gist of it is TEEs are very fast. They can offer secure computation, but if you're running a huge amount of data or confidential data there that has high risk, you would probably want to look at like an alternative mechanism. The other cryptography that people may have heard of, multi-party computation, the ability to compute over data, but having the key that is being used to do the computation shared among different entities in a way that each of them computes and none of them can actually see the origins of the data. It typically requires like non-colluding parties to work on it. It is definitely a good cryptography technology to offer secure computation. The key challenge with MPC is that there is a lot of communication overhead. And what it means is that if you have a limited amount of participants that do the computation, it works very well. We see it with wallets and custodians. But if you want to really move into like a decentralized environment where you have tens or hundreds of nodes computing together, this is where MPC actually is not very scalable, even though there are now progress quite a lot with like optimized protocols and garbled circuits, if some of you may have heard of it, as a faster iteration for MPC. And then we have the new kid on the block, fully homomorphic encryption, which is what we do. I call it as a new kid on the block, even though it's been out there for like 15 years. A funny story to say is like I was in Consensus last week, and we went and interviewed a couple of people and asked them like, what does homomorphic mean? Not a lot new. One even said that it sounds like a dumpling with pork and chocolate. But it is a very efficient cryptography that allows you to compute over encrypted data. So let's explain briefly like how it works. Encryption 101. Without homomorphic encryption, typically you have your key, you encrypt kept in Ethereum in that case, and you get an encrypted data. And when you want to decrypt, you just use the key to decrypt the data and you get the same result. FHE offers you now another layer. So you start by encrypting the data, but this time you encrypt it homomorphically. And now you can actually also compute over that encrypted data. In the example here, you have a prompt that says, let's change the color of the image from whatever this is, purple to black. And you get a result which is encrypted. So it is fully private from start to end. And then later on you can actually decrypt it and get the new output coming up. So it is quite powerful and enable you secure computation. And the good thing is that it's math-based. There is no trust assumption in any hardware components. So FHE, as I said, been out there for quite some time. It allows you to compute over encrypted data. Some of the key limitations that are typically associated with full homomorphic encryption is the scalability of FHE. It is definitely slower than the likes of trusted execution environment, even though there has been a lot of progression both in hardware, just running it on like CPUs and FPGAs and ASICs that make it significantly faster than before, as well as just newer FHE schemes like the one that we released like 2 weeks ago that just make it significantly faster. So in that regards, there's going to be a significant trajectory of even a faster full homomorphic encryption operations into the future. Okay, so let's say you're a builder and you want to build your confidential smart contract. What are some of the considerations that I would advise you to follow? And I think the first one is really to do data classification, meaning look at like what you're trying to build and try to understand within this data, which type of data is okay to be public, what type of data can be confidential, or selectively disclosure, like some of the data needs to be disclosed to some entities or others. The second part is build a risk model. So define who can attack your solution. What is your tolerance for leakage? If the leakage happens an hour after, is that still a problem? Is the data still valuable or need to be secured long term? And then of course the third thing is figure out your performance needs. Are you looking for a significantly high throughput, or are you okay with like 10 transactions per second? What is the latency that you need for each operation? And all of it will actually eventually define the type of solution that you want to use. Security level. We didn't talk a lot about the key that requires to decrypting the data. Verifying who holds the decryption key is like significantly important because your solution is only as secure as the ability to decrypt it. Making sure that the decryption key is not managed by a single entity and cannot be stolen is extremely important. I want to take like a minute to also talk about compliance. Many people have this assumption that privacy contradicts compliance. Like they think about it in like the old days, I'm adding privacy, and now I'm not going to be compliant. This is actually a question that we hear both from institutionals that are working from us, but also from developers that think about building. So compliance, and in my opinion, there's not like a set of regulation that we can follow, but the key thing to remember is if you're working on confidentiality of transactions, you can still do KYC and AML because we're not hiding the identity of the sender of the receiver. This is not like an anonymous solution. This is more about hiding the content of the transaction. So you can still verify, you can still do KYC and AML, which is extremely important in the compliance space. If you also need to add another tier, which is KYT, knowing your transaction, so have the ability to know the content of the transaction. Also here, the technology has been progressed so much that we now have a way to offer permits and define the set of criteria that would allow a third party, whether that's the regulator or the likes of Chainalysis, etc., predicate, to actually see the content of the transaction under certain conditions. So the technology now is no longer a barrier for compliance, and you can actually eat your cake and have it all. Like you can achieve both privacy and compliance. Infrastructure. Where do you want your solution to reside? Do you need to build it on a specific L1 or an L2 because that's where your target audience is? Or do you prefer to go where the builders are at or where the liquidity is, and now you actually want to achieve a solution that offers you privacy as a service with a coprocessor architecture? So figuring out like your base layer is extremely important because that will also define the type of solution that you want to work with. Do you want to go to like the Aztec or the Alio of the world, or do you actually want to operate like on Arbitrum-based Ethereum, and in that case, a coprocessor solution may be a better fit? And then last, and this is literally like my last thing, quantum safe. I know it seems like very far into the future where quantum computers still come. I see a significant growth and interest around figuring out which type of cryptography will allow you to be quantum safe in the long run. If your data needs to be secured for 2, 3, 4, 5 years into the future, you definitely want to start thinking about that now. Out of the different cryptographies that I mentioned, FHE is based on lattice-based cryptography, so it's quantum safe. There is work happening both on ZK and MPC that will allow variants of them that will be quantum resistant in the future. So is that like the key decision factor today? Probably not, but definitely keep it as part of your decision tree, especially if you're targeting institutionals. So just want to make sure, don't be the naked guy, be this guy, make sure that you're using confidentiality and that you achieve your privacy as a competitive edge. Thank you all.